So I think it's fine. Okay, so the content of this week's class will be quadratic approximation and constraint optimization. So let's get started with the content. So as always, these are the topics that I'll be discussing in this session. Quadratic approximation for a single variable function, then for a multivariable function. I'll be taking a couple of examples of each of them and solve those problems. Then I'll be going into the constraint optimization, and just a word of caution that in this session I'll be only discussing about the equality constraints and not the inequality constraints. So the inequality constraints and the penalty function method will be a topic of next week. So in next week's TS session that those two topics will be discussed. So let's get started. So for a quadratic approximation of a single variable function, fx, we have this kind of a formula if we want to approximate it in the point x naught. So fx is nothing but fx naught plus f prime of x naught, then multiplied by x minus x naught, then half times of f double prime of x naught, then times x minus x naught square. So as you can notice that you need to have the information about the first derivative and the second derivative of that function at the point x naught. And I'll be taking some problem now, and we'll be using this formula to solve those problems. So let's do that now. So this is the problem that I have for a single variable function. Fx is e to the power x plus x squared plus x cubed, and I need to approximate this function at x naught equals to 0. So let's see how I can do this. So let me do this. So first, let me write down the formula itself. So it is fx naught plus f prime of x naught, then times x minus x naught plus half times of f double prime of x naught and times x minus x naught square. So this is the formula that we have, and the function that I have right now is fx e to the power x plus x squared plus x cubed. Now, what I have to do, I have to find fx naught. So x naught is 0 here. So f0 is e to the power 0. So this is 1. Then I need to find the first and second derivative of this function. So let's find out the first derivative. So my first derivative, f prime of x, is e to the power x plus x squared plus x cubed. Now I have to also take the derivative of this term. So that's 1 plus 2x plus 3x squared. Now, I also need to find the second derivative of this function. So let me do that as well. So the first term remains as it is. And this part will be this again times 1 plus 2x plus 3x squared. And then I have this term times 2 plus 6x. So if you kind of rearrange and write it down, you will probably get 1 plus 2x plus 3x square whole square e to the power x plus x square plus x cubed plus 2 plus 6x, then times e to the power x plus x square plus x cubed. Now what we have to do, you have to find out f prime 0 or f double prime of 0. Those two you have to find out. So let's see how we can find that out. Okay, So still there haven't anyone, I don't see anyone in the class right now. Okay, so that's discouraging, I guess. Probably it's too simple, this week's content, or maybe it's like no one bothered to attend classes at Sunday afternoon. So it's either way, probably. So let's find this out. So this is e to the power 0, then this will be 1. So the rest of the part becomes 0. So this is e to the power 0, which is 1. And then you have to find f double prime of 0. So this is nothing but 1 plus 0 square times e to the power 0, then plus what you have 2 plus 0, then again e to the power 0. So e to the power 0 is 1, that's 1 plus 2, so this is 3. So now you have to have the final expression for the quadratic approximation of that function. So let me write down the expression again. So my fx now becomes fx naught, which is f0, which is 1, then plus f prime of 0, which is 1, times x minus 0, then plus I have that half term, and then I have f double prime of 0, which is 3, and then times x minus x naught square, which is x minus 0 square. So this is nothing but 1 plus this will be x, and this will be 3 by 2 x square. So this is the quadratic approximation that you achieve. So this is your final result for this problem. So using that formula, which kind of comes from the Taylor series expansion, you can have a quadratic approximation of any function. So that function was in terms of e to the power x plus x squared plus x cubed. And this approximation again varies from point to point. So as you can notice, if you put x naught equals to 0 or x equals to 0, so this function takes a value of 1 at that point. Here also, if you put x equals to 0, you can notice that that function takes the value 1 at that point. So you're kind of approximating that function at that point, so that function value matches at that point with the original one, but it kind of deviates at other points. So it's not like the perfect approximation that you can achieve, because anyway, one is an exponential function, other is just a quadratic function. But again, in order to solve problems like if you want to get to minima of some uh, function or maybe some optimality conditions you need to find out, quadratic approximation might help you, and you can solve the problem iteratively by approximating the function at like some stationary point. So it's kind of trying to find out the uh, function where zero value function. So it's like where the function takes the value 0. So that you will be trying to solve. Uh, so I think this problem will be pretty easy to solve for you. Similar kind of problem if that has been given. And yeah, so I still don't know why anyone hasn't joined. I don't know if this is some problem with my connection or system. I don't think so because I'm in this correct link as well. So yeah, anyway, okay. So that's the thing about uh, live sessions versus this kind of a session where I have to just solve problems on my own because I don't know whether you are understanding this or not. So yeah, anyway, I'll go on with the session anyway. Okay, so next is you have to find the quadratic approximation of this function fx e to the power x times cos x. So now you have exponential function multiplied with a trigonometric function. And again, you have to find the approximation at x not equals to 0. So you can notice that if you put x equals to 0, so it's e to the power 0 of cos of 0. So that's 1. So the function takes a value of 1 at the point x not equals to 0. So let me go ahead and solve this problem again. So the expression for the quadratic approximation, I'll write it down again. So this is fx naught times f prime of fx naught times x minus x naught times, maybe I'll write it as half. So this is half times f double prime of x naught times x minus x naught square. Okay, so now I have given the function. So the function is fx equals e to the power x cos x. So let's do this. So I'll write it down. So my f naught will be e to the power 0 cos of 0. So this is 1. And then what I have to find out the f prime of x. My f prime of x is e to the power x minus sin x plus e to the power x cos x. So I can write it down properly, e to the power x cos x minus sin x. Now I have to find f double prime of x. So this could be e to the power x times, so part will be minus sin x, this part will be minus cos x, and this part will be e to the power x times the same thing, cos x minus sin x. So that cos x part will get cancelled out, and you will be left with minus 2 e to the power x sin x. So I think I've written it correctly. So yes. So now what I can do, I can put the values 0. So e to the power 0 is 1, and the cos 0 part is, so this will be 1 times of 1 minus sin 0 0. So this part will be evaluated to 1. I have double prime of 0. This part, if you evaluate, it will be evaluated to minus of uh, 2 times 1 times of 0. So this part will be 0. So now what you have left with is a function which is not a function uh, of a variable which is having an order of 2, because your f double prime of 0 at that point has vanished. So now in this case what you are left with is, so fx now becomes your f0, so this is 1. This part, this f prime of 0, this part is again 1. This is times x minus 0. Then the rest of the part, it's half times 0 times x minus 0 square. So what you are left with is 1 plus x. Yeah. So this is your final answer. So you were trying to do some quadratic approximation at that point, but you ended up with a linear approximation at that point. So that happened because your f double prime of that function vanished at that point. So this kind of situations you also might arrive at while solving problems. So don't get confused like, where is my x squared term or something. If in some questions is given as your quadratic approximation at some point is a linear function, then that's totally fine, because probably the coefficient of the term, which is of x squared. Yeah, hi Diksha. So yeah, finally someone has joined. So I was discussing about quadratic approximation of a single variable function. So I think you have already noticed this formula in the class, in the lecture slides, and I took two examples where I had to solve like approximate a function at x not equals to 0. So one was an exponential function that I took and solved, and another I took as an exponential function and multiply it with a trigonometric function, so e to the power x of cos x. And the ultimate result that I got as quadratic approximation was a linear function. So that's what I was discussing, that if you approximate a function at some point, it might happen that the coefficient of the x squared term at that point becomes zero. So exactly that happened in that case. So that's why, so you need not like worry about whether the quadratic approximation is a linear function in some cases, because it might happen. So that's the kind of distinction that I was talking about. So I'll now go to the quadratic approximation of multivariable function. So probably I'll ask some doubts if you have, or maybe I'll solve the problem and ask you some specific value when I'll be solving. And hopefully others will also be joining later. So for a multivariable function, what we have this bold type notation, this x, x naught, these are vectors here. So vectors of this multiple variables, and instead of the first derivative, we have a gradient expression here, and instead of the second derivative, we have an expression of including the Hessian term. And I think in third slide, this zero point 0.5 was not mentioned, but actually there should be a zero point 0.5 here. And I think in one of the assignment questions also, the zero point 0.5 has been given there. So that's the correct one. So this is the expression that you need to use for this quadratic approximation of a multivariable function. And mind you, I think I have written it in a not a bold face. Okay, another one has joined. Okay, so yeah, so I think this x naught, I think I have not written it in bold face, but it should be a vector as well. So this should be bold. So I'll correct it and post it. So now let's try and solve a problem. And probably I'll ask you what will be the steps and on. So I have to approximate this function at this point xy equals to 1 comma minus 2. So I'll write down the expression. So in terms of x and y, this approximation expression will be f of x naught comma y naught. So it's similar to what I have in the previous slide, but slightly different way of writing it. That's all. So this part will be x minus x naught, y minus y naught. These are the two terms I'll be getting here. Then I'll be having this uh, grad of f x comma y, x naught comma y naught. And then the final term will be x minus x naught, y minus y naught, then my Hessian matrix at x naught comma y naught, and then this term x minus x naught, y minus y naught. So this is my expression, exactly like what is there in the previous slide. I've just written it in terms of x and y here. So now my function is given as fxy is x cubed plus y squared plus x squared plus y cubed plus 6x. Mhm. Yes, yes. This part, yeah, this part should be there, this 0.51. Yeah. That's what you are telling me? Oh, okay, okay, okay. Yeah, I have forgotten. Yeah, so here it should be a half here. Sorry about that. Okay, so this is fine now. Now, what I have to do, I have to find out the gradient at suppose this. So can any one of you tell me the expression of the gradient and the Hessian? So I'll put the values later on, but right now I'll just need to get uh, what will be here and here. So what should be the first term in the gradient function? Yeah, and there should be another term, right? So you said 2xy cube. Yeah, and the next term will be x2 y x cube. Uh, Sorry, like 2y x cube that you are telling me. It's the first term. Okay, yeah, correct. Yeah, next. Yes, this is fine. So what will be the expression for Hessian now? Oh, okay, okay. No problem. So I'll write it down just to check whether this is correct or not. So first I have to take with respect to x. So this will be 6x y square. Then the next term will be 2y cube. And then with respect to y, it will be 6x squared y. And the second term will be 6xy square. So I think this is correct. And the next term will be this this part will be 6x square y plus with respect to x it will be 6xy square. Yeah, so it will be symmetric. So that's fine. And with respect to y it will be 2 uh, x cube plus 6x square y. So I think this is correct. Yeah, so this is fine. So now what we have to do, we have to put this value 1 and minus 2 here to do. So this will be 1 and minus 2. So if you put the values here for this one, you will probably get first term will be 3 times 1 times minus 2 squared. So that's 12. The second term will be 1 times minus 2 cube. So that's minus 16 plus 6. And the bottom term will be 2 times 1 times minus 2, so that's minus 4. This will be 3x square y square, so 3 times 1 times 4, so that's 12. So ultimately what you will get is 2 and uh, 8 for your gradient, and for your Hessian you will probably get, so 3x again 1 and minus 2. So the first term will be minus 2 square, that's 4, so that's 24. That's next one will be minus 16. This one will be 6 times 1 times minus 2, so this is minus 12. The next term will be 6 times 1 times minus 2 squared, so that's plus 24. That's next, it will be symmetric one. So this will be minus 2 plus 12 plus 24. And the rest of the part will be 2 plus 6 times 1 times minus 2. So that's minus of 12. So this will be a Hessian matrix. So if I write it down, it will be actually 8, 12, 12, minus 10. So now you have everything with you. So it's just about plugging it back into the equation. And you also need to find f of uh, 1 minus 2. So that will be 1 times, so that's 4. Then next to 1 times minus 2 cube. So minus 2 cube is minus 8. And then plus 6. So this is 2. So now it's pretty simple. I think you have understood it. So this will be f1 comma minus 2. Then plus x minus x naught, x minus 1, y minus 2 will be, yeah, so this will be plus 2. Then this will be 2, 8. Yeah, and the rest of the part will be half x minus 1. Oh, sorry. Y plus 2. Then this Hessian matrix that you have with you, and this x minus 1, y plus 2. So be careful with the dimensions here. So this is 1 cross 2, this is 2 cross 2, and this is 2 cross 1. So ultimately we'll get a scalar. Here also, this is 1 cross 2, this is 2 cross 1. So ultimately we'll get a scalar from this part as well. So if you just plug in the values, you will get first term will be 2, then second term will be 2 times x this plus 8 times y plus 2. And the rest of the part, I think it's simple. You can calculate. It's just multiplication. So I'm not kind of wasting time just to calculate this. So ultimately, what you will get a quadratic approximation where you will have terms related to x, y, or maybe x square or y square, or maybe x multiplied by y somewhere. That's all. So the highest order of the terms will be 2 in all the terms that you get here in the final quadratic approximation. So you may be asked questions like, given a function, what will be the quadratic approximation at that point? You may be asked about only the constant. So it will be the constant value. So you'll just calculate that 2 and get this. You may be asked about the linear term as well. So something like this one. So I'll talk more about it when I solve the next problem. So let's solve this next problem. So here also it's a similar problem. I have like trigonometric functions multiplied together. So it's sine x times sine y, and I have to approximate it in the point pi by 6 or pi by 3. So again, as before, I can write a similar expression. So let me write it down just for convenience. So this will be x minus x naught, y minus y naught, grad of f x naught, y naught. This will be half x minus x naught, y minus y naught. This part will be x naught, y naught, and this will be x minus x naught, y minus y naught. So now if you are asked about the constant part, so this will be the constant part of the function. If you are asked about the linear term, so this part, the entire term will be the linear term of this function. And if you're asked about the quadratic term, this entire term will be the quadratic term of the function. So this is quadratic term. This is linear term. So you may be asked questions of this kind separately, and this is your constant term. So now your function is given as f x y, which is sine x sine y. Now, as before, you have to get the gradient and the Hessian. So it's not quite difficult to get. So the gradient is nothing but cos x sine y, and the next part will be sine x cos y. Yeah, and then your gradient, the Hessian calculation will be like this, minus sine x sine y. Then with respect to y, it will be cos x cos y. This is with respect to x, so this is cos x cos y. This will be sine x, so again minus sine x sine y. Yeah, so this is your Hessian expression. Now you have to put the values in here. So let's put pi by 6 and pi by 3. So in that case, what you will get, f of pi by 6 and pi by 3. So it's sine 30 degree multiplied by sine 60 degree. So this is half times root 3 by 2. So this is root 3 by 4. Similarly, for this one, you can get the values as cos pi by 6 times sine pi by 3, then sine pi by 6, sine, this is cos pi by 3. Okay, so this will be cos 30, it's root 3 by 2. This part will be sine 60, so that's root 3 by 2. This part is sine 30 half, cos 60 half. So this is nothing but 3 by 4, 1 by 4. So this is your gradient, and if you multiply it with that term, this x minus x naught and y minus y naught, you will get your linear term of this function. And when you try to find the Hessian, so what you are left with is first is minus sine x sine y, so that will be your minus root 3 by 2, sorry, root 3 by 4. And this cos x cos y part will be root 3 by 4 as well. And this will be again root 3 by 4. This will be minus root 3 by 4. So again, you have got everything with you, and you only have to plug this back here and have those multiplications, and you will finally get your answer for the quadratic approximation. And it's not too difficult to like multiply matrices or vectors, so probably you can do the rest of the part. So yeah, I'll just finish the rest of the part by plugging in the values. Okay. So that you can probably do later. So so that will be probably discussion mostly on quadratic approximation. So have you guys like seen the assignment? You have any doubt related to this portion of the material of this week? Otherwise, if there are no questions, I'll move on to the next part, which is the constraint optimization part. Or if you even have doubts from a previous assignment, you can ask anything related to like grading or anything you can mention here also. Not a problem. Mhm. Yeah, yeah. So you are saying solution of the previous assignments that you want the solution. Okay, yeah. Yeah, so I think what we can do, probably we can talk with the main TA, and probably he will be posting those. And if not, if you have some specific questions in from the this assignments, you can ask in the later TA sessions, like next week or something. Like then might be we might be solving it there itself. Like right now, do you have any specific? Okay, no. Okay, okay, okay. Yeah, sure, sure. Okay. So yeah, I'll talk with him and see if we can post it later in the course page itself. Okay. So I'll then move forward. So I think, yeah, one more thing I wanted to discuss in this topic. So that will be, you might be asked some questions related to the signs of the eigenvalues and whether you are getting a minima or a maxima or something like this. So what you can do, probably you are given some function f of x. X is a multiple variable vector. So ultimately what you will get, you can calculate the Hessian matrix of that. So that's h of x. And then you can calculate all the eigenvalues. So calculate the eigenvalues, or there are tricks to know the signs of the eigenvalues. So if the, okay, just a minute, I'll pause and come back. Okay, so, oh, sorry. Yeah, if the signs, okay, of all the eigenvalues are positive, then you have a positive definite Hessian matrix. And fx, mind you, is a quadratic approximated function. So this has to be a quadratic approximated function. Then only will have the property of convexity and all. So now what you have, uh, this positive definite Hessian matrix. So that will imply that if you solve the optimal for the optimal point of the function fx, then you will get a minimum. Similarly, if the signs of all the eigenvalues are negative, then you have a negative definite Hessian matrix, and you have a maxima. And finally, if you have, uh, suppose you have two eigenvalues, lambda 1 and lambda 2. Suppose one of them is greater than 0 and the other is less than 0. So it might happen that either of these two cases, then you have a saddle point. But if one of them is 0, then you cannot say anything, or lambda 2 is 0, no conclusion can be drawn. So you remember this properties. Probably you were asked one question related to this. You don't need not have the proof of this because that's a bit dense. But I think if you just know these properties, you can solve those problems. So that's not an issue. And I think there are some proofs online here. Online, if you just search it up, we'll get the properties of eigenvalues of Hessian matrix, and then you can get related to minima, maxima, and saddle point, and you can get the proofs and all. If you're interested, you can have it for further read as well. Okay, so that's mostly from quadratic approximation, and the rest of the portion, I think that's pretty easy and you can solve problems easily. So let's move on to the constraint optimization problem. So this is for equality constraint. So let me ask one question. So have you two of you seen the assignment of this week? Like, have you gone through all the questions yet? Hello, I didn't hear you. Like, Okay. Okay, okay. So did you notice something unusual, like some question maybe from outside of what has discussed in the class or anything? Okay, 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 okay. Uh, okay. And what about you, Jay Surya? Have you tried? Yeah, yeah. So, like specifically, have you found like problems specific to some questions or anything? Uh, okay. Yeah, yeah. So that's correct. So actually, in the class, what Sir discussed in this week's content, it's for only equality constraint. But in one of the, I think two of the questions in the assignment, there were inequality constraints that was given. So inequality constraint is the discussion of next week. So probably we won't evaluate those two questions because anyway, that's not part of this week's assessment. But if you can just go through next week's lecture and solve those questions, that would be fine as well. And I think one of the question also has a typo in the options somewhere. I think some Z max is being asked in one of the questions. So that's the maximum value of the optimal point. Uh, so that question is wrong, I think. So when you try to solve this, just keep those in mind that there are a couple of questions having this issue. Okay, so as I mentioned, I'll be only discussing equality constraints today, and in the next week, I'll be discussing that inequality constraints part and the rest of the part that will be covered in the next week's lectures. So as you know that earlier this will be a minima point in the unconstrained version, but now you have this curve gx equals to 0. So that means your minima kind of shifts to here. So we have already seen, I think you have gone through the lecture, and this way you can write the Lagrangian. So this is also this Kuhn-Tucker's method, but this is for equality constraints only. So the necessary conditions here is that after writing the Lagrangian, so Lagrangian is written in terms of this function which you minimize. So I think in first slide it was given as minimize or maximize. So if you are given a maximization problem, I'll suggest you to just convert it into minimization problem by multiplying it with -1. So that will be the standard form, and then you can apply this formulas. So suppose you are given minimization of fx subjected to this equality constraint. So you have bunch of equality constraints. So there are m number of equality constraints here. So for those, you introduce this variables lambda 1 to lambda m and multiply them and write it in terms of like addition, and this is your Lagrangian. Then you take the derivative with respect to every variable, so from x1 to xn. So this is for all I. So this is 1 to n. So you have n number of equations here, and this part is for all j's. So j goes to m. So you have m number of equations here. So finally, what you get when you take this partial derivative with respect to lambda 1 to lambda m, you get back g1 x equals to 0, g2 x equals to 0. So this is your this equation only. But only thing that's been of interest here, it's this first equation where you take the partial derivative with respect to x. So now let's see some problems, and I'll be probably discuss some 15-20 minutes more today to complete this part because anyway a few of you like joined late, and also I could not, I had to start like 5 to 10 minutes after delay happened because there were issues with my laptop and all. So let's solve this problem. So I have to find the Lagrangian of this following optimization problem, where it is given as a minimization problem. So that's not a problem. And I'm given two equations. So what I can do, I can introduce lambda 1 here and lambda 2 here. And I can write these equations in terms of 4 minus x1 minus x2 equals to 0. And this one I can write it as 5 minus x2 square minus x3 square equals to 0. So this is your gx equals to 0 kind of terms. You can also write it as x1 plus x2 minus 4 equals to 0. It's just the signs of lambda ones will be flipped in those cases, but that's totally fine how you can write how you are writing this. So the Lagrangian will be pretty simple in this case. So it would be a function of x1, x2, x3, and lambda 1 and lambda 2, as I have mentioned in the previous slide. So this part will be your fx. So that's x1 square plus x2 square plus x3 square. Then you have this lambda 1 times 4 minus x1 minus x2 plus lambda 2 times 5 minus x2 square minus x3 square. So this is the expression of your Lagrangian. This part can be a bit different also, depending on how you take this equality constraint. So when you are given some multiple choice questions and probably you might see that the signs are not matching, so you might have to write some equations in a flipped manner. So just be careful with that. So is this part clear? Do you guys have any questions? Otherwise, I'll move on to the next problem where I have to solve the problem for optimization. Okay, so this is fine, I guess. So now I've given this optimization problem where this you have to do minimization of x squared plus y square, and I'm given this function, this constraint function. So now I have to write the Lagrangian first. So can any one of you tell me what will be the Lagrangian of this function? So it will be a function of x, y, and lambda. So what will be the first term and the second term? Something like that. So if you have understood the previous problem, I think it should be pretty easy uh, on how to write. So you can refer to uh, this equation. So now I'll go to the back to the problem. Now tell me what would be the terms. Okay. I don't know why there are so many doubts. Like this will be fxy. This will be lambda times gxy. Yeah. Now can you tell me what will be the this expression? Okay. So your fxy is given as x squared plus y squared. So I think probably you have not memorized it. So yeah, go back to the lecture after probably this session and then maybe try to relate it with how I am solving it because otherwise you won't understand. So later on, I think I have to do some work to understand this. So this is lambda 1 times 21 minus 3x minus 5y. So this part I'm writing it in terms of this equals to 0. So now I have to take the derivatives, the partial derivative with respect to x. So now this will be 2x minus 3 lambda. So this I have to set it to 0. Then I'll have another equation with respect to y. So that will be 2y minus of 5 lambda. And so this will be 0, this will be 0. So your x will be 3 lambda by 2, y will be 5 lambda by 2. And finally your del lambda, that will be 21 minus 3x minus 5y equals to 0. So you just put the values of x and y here in terms of lambda. You will get uh, something like this. So this will be 17 lambda. So 9, yeah, 17 lambda equals to 21. So lambda will be 21 by 17. And finally, what you will be left with is your x will be uh, 21 by 17 multiplied by 3 by 2, and your y will be 21 by 17 times 5 by 2. Yeah, so this will be your final answer. You plug this x and y value and you will get the optimum solution here. So this is pretty simple. So that's how you solve the problems with equality constraints. So let me take another problem. Okay, just a minute. Yes, I have a couple of problems with me. I think I'll discuss those two and probably will wrap it up in 10 minutes time. So this one also it's similar problem. Again, you have to write the Lagrangian here. That will be a function of x1, x2, x3. And for this equation, you will have a lambda 1. For this one, you will have a lambda 2. So it's again pretty simple that you have to write the function first. That's your fx function. And then just lambda 1 times this first equation and lambda 2 times the second equation. So this is again simple. Again, what you have to do, you have to do del L of del x1 equals 0, del L of del x2 equals to 0, del L of del x3 equals to 0, and also del L of del lambda 1 equals to 0, and del L of del lambda 2 equals to 0. So ultimately, you'll be left with 5 equations here, and you will have this x1, x2, x3 in terms of lambda 1 and lambda 2. Then you can solve those, I think, this lambda 1 and lambda 2 equations, and then you can get your x1, x2, x3 values as well. So here you have 5 unknowns and you have 5 equations. So you can solve this problem. So it's just writing the Lagrangian and then taking the partial derivative with respect to every variable and just solving it. That is the only part that's been involved here, and it's again pretty simple to solve. So I'll probably have one or two more problems. Yeah. So there is another problem. Suppose I am given this kind of a problem. Let me ask you two. Can you notice this constraints and see some patterns to this constraints here in this problem? Like, do I need all the three constraints, or like if I take two of them or maybe one of them, I can still have the same kind of a problem? Okay, in such problems, what you can notice is that suppose you take lambda 1 here, lambda 2 here, lambda 3 here. Okay, so let me write down this Lagrangian. This will be x1, x2, and x3, lambda 1, lambda 2, lambda 3. So you will have six equations and six unknowns in this case. First I'll write the Lagrangian. This will be the function, then lambda 1 times 2x1 plus 3x2 minus 13, lambda 2 times x2 plus x3 minus 4, plus lambda 3 times 4x1 plus 8x2 plus 2x3 minus 34. So here also what you have to do, del L of del x1 equals 0, del L of del x2 equals to 0. So you have to calculate those expressions. I'm not writing it entirely. Then this part will be del L of del lambda 1. Okay, yeah, so this will be del L of del lambda 1 equals 0, del L of del lambda 2 equals to 0, and del L of del lambda 3 equals to 0. So you will have six equations and six unknowns here. But can you do better in this situation? So if you see these three equations, what you can notice is that if you combine this first two equations, suppose 2x1 uh, plus maybe what I can do, yeah, 3x2 minus 13. Suppose I multiply this by 2, and then second equation that you take, you multiply it with 2 again. So what you are left with is this this 2x1. So this is 4x1 plus 6x2 minus 26 plus 2x2 plus 2x3 minus 8. So this part is nothing but 4x1 plus 8x2 plus 2x3 minus 34. So if this first two terms are zeros, and you are just multiplying it 2 by 2 and you are adding it up, so this will also be 0. So that means you don't need this third equation here. This is kind of extra. You can just have a lot of combinations of the first two equations itself, and you can arrive at that third equation. So since that's unnecessary, what you can do, you can drop that, and you need not solve this problem with this lambda 3 term anyway. And here you can just set lambda 3 to 0, and you need not bother about this equation. And for all other equations, you set lambda 3 equals to 0. And then you can proceed and try to solve this using five equations and five unknowns. So that's one additional check that you can do while solving this constraint optimization problem, whether one extra constraint is actually having some effect in the final solution or not, or the constraint space or not. So that's this thing I wanted to discuss. Yeah, so this is fine. Yeah, I think I have reached the end, but yeah, couple of discussions I wanted to do. One is for inequality constraints. Now, suppose I can always convert my inequality constraints to equality constraints. Suppose I am given this 2x1 plus 3x2 plus 4x3 less than equals to 9. Suppose somewhere I am given this constraint. What you can do, you can just add some slacks here. So this 4x3 plus say s equals to 9. So this s is now greater than or equals to 0. So now you can have a similar approach to solve this kind of problem. You will take another lambda, uh, And then while writing the Lagrangian, you have the first fx part, then you will have this lambda times gx part. But now, if you noticed, you have something extra here. So this is s that you have written. So now your fx is nothing but lambda times, and then this lambda times of s. So you kind of have some extra effect now because of this inequality signs. So that has to be taken into account while doing the inequality constraint optimization. And there you can notice, or maybe right now you're not able to, but later when you go through the next week's content, you will be able to notice that you have some restrictions on the lambdas right now. So this lambdas cannot be negative in those cases, so it has to be some greater than equals to zero. So those cases has to happen, and if we take this as greater than equals to zero in our Lagrangian itself, what we can do, I think I have not written a minus 9 here, so there should be a minus 9 as well. Yeah, so in those cases, you can just ignore this term from your Lagrangian and just consider this term, but you have to have this lambda greater than equals to extra constraint in your equation. So that's the main idea, like mathematical background of inequality constraints. So later, I think when I go through the lectures, you'll be able to understand. So in next week, I'll be discussing this inequality constraints problem, as well as I think sir will be discussing penalty function method in the lecture. So I'll be going through those penalty function methods as well. So with that, I'll stop, and I'll also be communicating with the TS so that uh, they can post the solution as well of the previous assignment. So I think there is one TS session right now, so you can join that, and probably there is another session with the course instructor itself, maybe tomorrow or sometime. So do join that as well. Okay, so if you don't have any questions, you may leave and join the other meeting.